Welcome back. Today we're covering doubly linked lists. I've already made the starter code below, which is just a copy of our singly linked list, but with a new name. That's because they're overwhelmingly similar. Now we're going to make our changes that make it doubly linked. Starting in our node class, we simply need to add a new variable and corresponding methods. So right below our node next, add a node previous. Then add it to our constructor, and then add hasPrevious, previous, and setPrevious methods just like our next ones. So copy, paste, and change the word next to previous. And that's it. Now we have a doubly linked node. And what comes next? Well, going into our doubly linked list, we can actually make a bunch of modifications to our existing code, but the interfaces will stay the same. Going down from top to bottom, we'll start with our add method. And since all we're doing is adding to the end, it's actually pretty easy. We've already set our old tail to point to the new tail, and now all we need to do is have our new tail point to the old one. Done. Now we're going to add first. We're currently resetting the head and where it points to, but we know in doubly linked lists, this goes both directions. So we also need to take our last head node and set its previous value to the new head. And that's it. Added a location. This one's going to be our trickiest because we not only need to change our next pointers, but also the previous pointers. So let's loop to I, same as before. And before we do temp.setNext to the new node, we're going to do temp.next to retrieve it, and then set the next node's previous node to the new node. And then everything else is the exact same. This means our node at index I will point its previous pointer to the new node, and then our I-1 node will point its next pointer to the new node. And we've instantiated our new node with temp.next and temp for next and previous, so we're good to go. Really, these modifications haven't been that bad so far, and really singly linked lists are kinda crap compared to the simplicity of a doubly linked list, but they do serve a purpose, but we won't worry about that now. Let's go on to remove. This one's a bit more complicated, but still easier than our singly linked list. So let's go to our ith node, and then we'll do our toRemove.next.setPrevious to temp, and then temp.setNext to toRemoves.next, which kind of does what we did in our add, but just removing the node instead of putting it in there. And then we'll do toRemove.setNext null and toRemove.setPrevious null to remove all the pointers from it. Again, not too hard. Now for remove first, we're 99% of the way there. All we need to do is do this.head.setPrevious is null. And with remove last, we can actually just get rid of almost everything other than the size decrementer and do this.tail equals this.tail.previous. And then if this.tail does not equal null, this.tail.next.setPrevious is null, this.tail.setNext is null. Way easier than we had in our singly linked list. And then get a location, get first, get last, next, has next, all of these no changes whatsoever. But we do need to add a previous and has previous method, which will just copy and paste our next and has next, and then change all of our next to prev, and that's it. All of this has been super trivial, which is pretty awesome. Lastly, for index of, we don't need to change this because it does work as is, but there is something we can do to take advantage of the fact that it's doubly linked. We can check both sides of the list at the same time and then move inward. This will take half as much time to run, and it shows off a really cool strategy of looking for a crossover point, which will come in handy during algorithms later on. So let's do int I equals 0, int j equals this.size minus 1, create temporary versions of your head and tail nodes, and then we're going to do a while loop, while I less than j. Now, if our tracker node for the front node is our object, then we return the index I, and then copy and paste this, but now check the tail tracker, and if it matches, return j. If it's neither node, we increment I, decrement j, and then we're going to move our front node forward one, and our tail node back one. This will loop until the nodes cross over, and then it'll quit, and then we'll return -1 if we still haven't found it. But there's one last check. What happens if our list length is odd? Well, we'd eventually hit I equals j, and we'd quit, but we wouldn't have checked the node, so let's just throw an equals on that less than for less than or equal to's, and now we're actually done. Before we test this code, let's do a quick validation sweep. Looking at each method, we want to make sure we're accounting for when values might end up null or not. I'll let you experiment on your own here, but the one thing I do want to point out in order to get our base case running is this remove first method. What happens if you only have one node? Well, now you're trying to mess with a null head's value's previous value, but we remove the old head. So let's wrap this logic in an if this.head does not equal null, just to be safe. Now go to our data structures test class, change singly linked list to doubly linked list, run it, and voila! Our base case is working with a new doubly linked list. Life is way easier this time around, isn't it? The logic is either tiny modifications, or simplifications, or performance boosts, compared to our singly linked lists. A singly linked list is great if you want to enforce single traversal in a one direction, but for more general use cases, you're going to want to use a doubly linked list. They take up a little itty bitty bit more memory to store that pointer to the previous node on each node, but they're way faster to the point that even Sonic is blushing. And let's tune in next time to find out how we can make both of these two linked lists circular. Like, subscribe, and comment below what you want to see next or topics you'd like to know more about.